Hi, everyone. Is this on? Yep. Hi, everyone. My name's Sebastien. I'm the Phison CTO. It is a pleasure to be talking with you today, which is actually kind of neat because I do a lot of these conferences and often the attendance is quite small. For the non-keynote sessions, this one, there's actually quite a few people in the room. And so I'm happy to be here. We're going to start off with the presentation where I cover my material. And then if you have any questions, I would be happy to answer them at the end of the presentation. Or in fact, if you want to interrupt during the presentation, that's fine too. So I'm here to talk to you about small language models, or SLM. And one thing to keep in mind is that small language models are like large language models, but smaller. They're still transformer architectures. So I'm here to talk to you about the trade-offs, particularly for edge-based AI, and the performance, the accuracy, and the efficiency that's possible with SLMs when they're paired properly and selected properly for the task at hand. So my name is Sebastien. I'm the Phison CTO. Phison as a company, we've been making SSDs for over 25 years. We make complete products and we compete with some of the more well-known brands from the NAND vendors. We make equivalent products that are as good, and I like to say a little proudly, often better than what you can get from somebody else. So we've been doing this for a long time. Recently, we found that SSDs can actually participate in the AI ecosystem, and we've got a whole product line that goes with this that we call aiDAPTIV. But first, let's talk about SLMs. So a small language model, an SLM, is essentially like a large language model, but smaller. People typically define SLMs as being in the range of about 500 million tokens to about 14 million tokens. And the idea is that we're not going into the really, really big models, the 70 billion, the 100 billion, the 600 billion. And these smaller models can actually run really, really well on, these smaller models can actually run really, really well on edge platforms that have limited resources. And so they can actually go into kiosks. They can go into a lot of different situations. Now, one thing to keep in mind, because when we say, well, let me approach this a little differently. If I were to tell you that it takes 400 milliseconds for the system to respond, most people would say, what? That's unacceptable. Now blink your eyes. That's 200 to 400 milliseconds. So from a human perception standpoint, 400 milliseconds is nothing. You blink your eyes, you pause to think about a thought for a second, that's 600 milliseconds. So keeping in mind, if we're interacting with other high-speed embedded systems that need responses at the millisecond or microsecond level, sure, yeah, that's, waiting 200 milliseconds is not great. But if we're talking about interacting with human beings, anything that is 200 milliseconds, 400 milliseconds or less, you won't even notice. So then the second thing to consider is how many words per second can a human read? And the answer is about 4 to 5 for the average person. And so if an LLM is outputting words about 4 or 5 words per second or faster, from your perspective, it will outpace how quickly you can read it. And so you're never stuck waiting for it. And having that frame of reference of human perception is important when evaluating what small language models do on edge solutions from a user interaction standpoint. Now, I just realized this morning I made a mistake in the division. I went the wrong way. 7 tokens per second is not 9 words. It's closer to 5. I divided by 0.75 instead of multiplied by 0.75. So I'll fix that in the slides when I get it, when I return the slides. But it does not change the conclusion. So, so from a large language model, every time you generate a token, you have to run the whole model, or you have to run the token through the whole model. And so that turns into a bandwidth constraint problem, which is something that all language models encounter. So if we assume that we have 100 gigabyte per second DRAM bandwidth, which is what you'll see on a typical PC and it's very achievable in an edge system, what that means is a 14 billion parameter model can generate about 7 tokens per second, which is not 9, but 5. And 8 billion will generate 12, 4 billion will generate 25, and 0.6 billion will generate 166 tokens. Anything above about 4 words per second, which is pretty much all of them, will generate a good user experience. But the ability to generate more tokens per second is always appreciated, but that's part of the reason why the 14 to 0.6 billion parameter model is considered small. It's because it's something that can fit on an edge system. So the main takeaway from this slide fundamentally is that small language models can actually produce a very good user experience. Now, the question is, how good is it? And for that, we can look at benchmarks. What I have on this slide above in the upper right-hand section is a collection of all the open source models that fit into the general category of SLM. There are variants of all of these, some that are optimized for reasoning, some that are optimized for instruction following, but this is a good sampling to kind of tell you where they're at. So let's consider the MMLU benchmark. And what is that? You know, it has a fancy name, Massive Multitasking Language Understanding. Great. But what does it mean? Look at the question at the bottom. So, you know, because we hear, oh yeah, there are questions and the AI has to figure out how to answer them. What do they look like? Because the model has actually has quite a lot of questions that cover a wide range of stuff like law, medicine, ethics, and they all require some amount of reasoning, not just language processing, not just fact retrieval. And so, one of the questions that I picked up from the set of questions that are available is the plura. And then you have 4 to choose from. They have no sensory innervation, separated by 2 millimeter space, and things that are not like, there's no obvious answer like a lot of multi-choice quizzes look like. Often there's an obvious answer. There's no obvious answer unless you know what a plura is. So if an AI model can kind of discern what the most correct answer is, it will have a response better than 1 over n, which is essentially 1 over 4, 25%, which is what it will guess if it's just randomly picking an answer. And what we see, and I've drawn a line at the 25% mark to show that there are quite a lot of models that are clearly doing better than random selection, which is kind of cool. If we actually go a little bit deeper into that and say, hey, it's nice that some models are better than random guessing, but we'd like to have something that's actually pretty good. So a high quality answer. So we look at the 60% mark, and here we see there are this one is 5. 5 models that stand out. 3 of them are related to Qwen, which is a model released by Alibaba. One is from Microsoft, 5.4, and then the third one is for Gemma 3, which is from Google. So all of those models, despite the fact that they're only in the 14 billion to 4 billion parameter range, do really, really well in these actually pretty challenging questions. And so this highlights the importance of not just picking a model at random or just picking a model because that's what the previous team did, but rather evaluating them for the problem that you're trying to solve and actually taking some time to quantify or to calibrate the responses that are being generated to see, does this meet my need, or should I be looking at a different model? In the AI sphere, there are probably a good 10, 15 models that are used as a kind of abstract way or a neutral way of evaluating models, which it doesn't mean just because a model did well on one test or another test that it will do well in your environment, but it's a nice, consistent way of evaluating the models and showing the ones that have more potential. And then you also look at the benchmarks that are being evaluated and see, is this close to the problem that I'm trying to solve? And so if we factor in the same model, but we add a second column for each model, the dark orange one, which represents GPQA. GPQA is Google Proof Question and Answer. And what that basically means is that if you were an average person, you were given Google and the questions, and you had about 30 minutes per question, the average person would score about 34%, and a domain expert with PhD level knowledge will score about 74%. So in that scenarios, and here we put the bar at 50. You could set the bar at 74 if you want. The small language models are not designed to handle these problems. They're not really intended to, and yet a few of them really stand out as being very good candidates. And so again, that highlights that small language models do have a place in edge systems. But there are certain things that small language models are not good at. And so here I highlighted some of the benchmarks that are commonly used where small language models do horribly at. And they tend to be agentic workflows, complex instruction following, or very long context. These small models do not do well. So again, understanding what you're trying to do with your edge system and picking the right small language model has a really nice is very important in the path where you're trying to select what it is that you want to do to solve your problem. Now, one of the problems that we encounter when running edge solutions is that these systems don't have a lot of memory. A 2 billion, a 4 billion parameter model needs a minimum of, I'll say 4 gigabytes to store 4 billion parameters. Then there's the activation memory, which will add another 1 or 2 gigabytes of memory. And then the KV cache, which is important for actually having a good user flow when running that small language model. And so when you're stuck with a limited amount of memory, you have a couple choices. Either you limit how many users can actually interact with the system, or you pay more or you increase the BOM cost of the device to actually have more RAM, or you can actually look for another way of getting a RAM pool using a traditional solution like offloading to the storage media. And so here, what we have with our adaptive solution is this idea where we create a unified pool of memory, where the GPU memory, whether it's HBM or GDDR, the CPU DRAM and the SSD can all be combined to work together to provide a more effective solution than when you're only leveraging the GPU's internal memory. So our solution actually fits under PyTorch. And it essentially takes care of doing all the data movements to essentially make it transparent to PyTorch. And it's paired with 1 or 2 SSDs. Now here we're showing an M.2 2280. We can make them much, much smaller. We can put it into a BGA form factor. There's a lot of stuff that we can do to both bring this cost and the form factor down. But here we're just going to show the sort of standard solution that we have. And when you're talking about a KV cache, and I'll go into a little bit more detail on the next slide, but when you're talking about a KV cache, essentially the way inference works is that you first run all of you first start by taking your query and all the input material, you tokenize it, and then you run each of those tokens through the large language model to generate your first output token. And then to generate your second output token, you run all of the input tokens and the first output token to generate number 2. And then you do that for number 3, number 4, number 5, which basically means all of these matrix multiplications will be happening again and again and again and generating the same results over and over again. And the way that we've solved this problem traditionally for the last 40, 50 years is to say, hey, we're reusing the same calculations. Why don't we cache them? And that's all a KV cache is. It's a cache applied to the AI calculation problem. But the KV cache is not small. So if we're looking at, for example, Qwen 3, and I picked the top 4 models throughout the previous slides. So it's 3 of them happen to be Qwen 3, and one of them is 5.4. I didn't include the Google model, but it would be in this range, essentially, just a little bit less. It'd be between 5.4, 14 billion, and Qwen 3, 8 billion. That's where that row would go. But each KV cache entry is anywhere from 46 kilobytes to 82 kilobytes. Now, if you were to have, for example, 2,000 tokens of input, 200 tokens of output, that gives you the middle column. And then if you're supporting 20 users, you just multiply those numbers by 20. So we're talking anywhere between 2 gigabytes and 3.5, 4 gigabytes of memory to be able to hold that small subset of interactions. So again, that's adding more and more to your required RAM footprint in order to be able to get that acceleration. Now, our solution, what it does, because essentially once you run out of that memory, you end up with the situation that we have here where we show the first row is standard and the second row is adaptive. There are a couple ways that you can end up here. So prefill is the same for everyone. You always have to do the prefill calculations. But then the question becomes, once your session goes on, what happens if you no longer have those necessary tokens in the KV cache and you actually have to run them or recalculate them? So then essentially if you're recalculating 1 kilobyte of KV cache, that's about 6 seconds of time in this scenario. 2 is twice as much, and 4 is 25 seconds. 8K of tokens is 55 seconds. And that would actually be 55 seconds that you sit there, a minute, and there's no output. With our solution, the time is almost flat. It's not actually flat. It goes up, but it goes up so slowly that, as you can see from the graph, it's quite flat. And so what we're doing in this scenario is basically saying, when a token falls off of the KV cache, instead of just being gone, we capture it and put it in the SSD. And what we do is we capture all of those tokens. And when I mention that, people say, well, why don't you send it to DRAM? I mean, wouldn't that be faster? Sure, but DRAM's a lot more expensive. But actually, it turns out it's not that much faster. And I show that on the next slide, which is to say that there's almost when you have a very, very good implementation, there's almost no difference between pulling from the SSD and pulling from the RAM. But the other benefit of actually having the KV cache on the SSD is we don't have to delete it. We can leave it there for a month, 2 months, a year. If another query comes in that essentially matches the input, we actually will get a hit on the KV cache lookup and retrieve those tokens. So what that means in practical terms is that you can start interacting with the system, go away, come back tomorrow, continue your interactions, and you'll still get that efficiency that you had from all the previous conversation. You don't have to wait or regenerate that conversation. You can just pick up where you left off. We can actually store hundreds and in some cases thousands of past conversations and then delete them too as needed. But unless there's a specific directive to delete them after a specific time, the SSD would just hold on to them. And so that again goes to create a nice user experience where they go away from the system, come back, and it just picks up where it left off. And that's not possible when you're limited to a small pool of DRAM. So here we did a crazy stress test where we took our architecture. Now, this is not an edge configuration. Edge configurations do not have NVIDIA H200 GPUs. But that wasn't the purpose of this test. The purpose of this test was, do we have inefficiencies in the system that would actually degrade our performance? And the short answer is no. I mean, we did initially, but we worked all of those out through just normal debugging and maturing of the product. And if you start by looking at the bottom row where it says GPU HMB, in the H200 configuration, it can generate 781 tokens. So that's the best performance as possible. And if you look at the top row where KV cache is turned off, it generates 464 tokens per second. And so that gives you the range. And when we're running our adaptive solution, whether we're offloading the SSD or DRAM, we're about the same range of 624, 27 tokens per second, which is within about 10, 15% of just running everything out of HMB. So here we're basically showing that whatever your solution is, we perform really, really well. And then a question that comes up is, great, how are you compared to the open source solution? And the answer is we're about twice as fast. So which is not a dig on anybody else's solution. It's just a comparison to say that, hey, we're competitive. And when it's done right, users will not really see the difference whether the tokens are coming out of the SSD, out of DRAM, or out of HMB. And so, that is my last slide. And the key takeaway that I want to give you is that our adaptive solution creates a unified memory pool. It's easy to use, cost effective, but also that small language models actually do have a place in commercial deployments when they're paired properly with the task at hand. And with that, I thank you for your time. And if you have any questions, I'd be happy to answer. Yes, go ahead.
Okay.
Yep.
So, yeah, thanks for the talk. I was wondering, there's a concentrated effort in the data center world, and there were presentations. The one that comes to mind was SK Hynix from yesterday on PIM processing in memory.
Huh?
On the edge side of the house, yeah, your adaptive strategy today is primarily focused on unlocking efficiency or optimizing available efficiency on the memory footprint side relative to KV cache.
Mm-hmm.
Since you manage research, do you see a forward-looking opportunity where part of the compute, the PIM effort so far, what was presented at the conference yesterday was restricted to DRAM. I understand this is more flash SSD.
Right.
On the edge, part of the matrix multiplication compute also migrating to the SSD side. Is there an opportunity there, or do you perceive an opportunity? If you could give some color and context on that, I'd appreciate it.
Yeah, and it wasn't originally part of my presentation, but there's a lot more to our adaptive solution. So, for example, when you're doing training, there's a forward propagation, backward propagation, and the error reduction phase, or the gradient descent, which then turns into the update flow. That step by itself only requires vector-vector math and can be implemented with a DSP. One of our upcoming SSDs actually has a DSP integrated into it. And when we move that update flow as part of, so for the inference side, it mostly, so the train, so what I would just to finish the statement, when you do the training side, you have an offload scenario like we do with our solution, you're about 40% faster. So we have that on hand. We're also in the process because you were asking more about generic compute, we're also in the process of bringing NPUs into SSDs where they can actually house the model locally and actually run the model locally. And then we can do other things. For example, like the model and all the weight set is always encrypted on when it's moving between the source and the destination. When it's on the SSD, it's only decrypted on the NPU. And so there's a lot that we can do for security standpoint and isolation with that flow. But specifically for inference, you're asking, could we do something on the SSD? Not really, not yet anyways. What we're focusing on from the SSD standpoint is just, oh, it's telling me I'm done. From the SSD standpoint is just making sure that it's as efficient as possible. And so we're going from Gen 4 to Gen 5 to Gen 6 in that speed flow. No problem. All right. Looks like there are no more questions. So thank you so much for your time. It was a pleasure talking with you.